Hello everyone, this is BB Sangmay, and in this today's video I am going to discuss about Soderberg and Goodman diagram. Okay, do subscribe for the upcoming videos of machine design. So when a component is subjected to fluctuating stresses as shown in figure, so this is the figure of fluctuating stresses. You can see that there is a mean stress, so this is the mean stress sigma mean, as well as a stress amplitude sigma e. Okay, so here you can see that there is a maximum stress also sigma max, there is a minimum stress sigma mean. Okay, so it is observed that the mean stress component has an effect on fatigue failure when it is present in combination with alternating component. Okay, so here the fatigue diagram, let me show you the fatigue diagram. So this is the fatigue diagram. Here you can see that this is the fatigue diagram. On the fatigue diagram you can see that the mean stress, that is sigma mean, which is the average of sigma max plus sigma minimum, is plotted on the x-axis, that is abscissa. The stress amplitude, that is sigma a, in case of a fluctuating stresses, sigma a is plotted on the ordinate, that is y-axis. So here the magnitudes of sigma m, that is sigma m is nothing but sigma mean, and sigma a, that is stress amplitude, it depends on the magnitude of maximum and minimum force acting on the component. Okay, so here you can see that in case of fluctuating stresses, sometimes the stress amplitude is above the mean line, so which represents the maximum stress, and sometimes the stress amplitude is below the mean line, which is the minimum, that is the minimum stress which is acting on the component. This is because of the maximum force and the minimum force, or the maximum intensity of maximum force which is acting on the component, and intensity of minimum force which is acting on the component in case of a fluctuating stresses. Okay, so here you can see that if the stress amplitude becomes 0, what will happen if when a stress amplitude becomes 0? In that case the load becomes purely static, it will not change with respect to time in magnitude or direction. Okay, when sigma a becomes 0, the load or the force which is acting on the component, it will be purely static, and the criteria of failure will be totally dependent only on the yield strength or the ultimate strength of the component, which is checked during the tensile testing. Okay, but we are dealing with the fluctuating stresses and reversed stresses. Okay, so here you can see that the yield for the when stress amplitude becomes 0, the criteria of failure becomes on the basis of yield strength in tension and ultimate strength in tension. So here on the x-axis you can see that this is the Soderberg and Goodman diagram. On the x-axis you can see that yield strength is tension and ultimate tensile strength is plotted on the x-axis, that is the abscissa. Okay, but when mean stress, that is sigma mean, which is the average of sigma maximum and sigma minimum, when what will happen when the mean stress becomes 0? Here you can see that when the mean stress becomes 0, the curve will pass from the x-axis or from the on the axis, that is abscissa. So here you can see that the when mean stress becomes 0, the curve will look like this. So this is the example of reversed stresses. So when the mean stress, that is sigma mean, becomes 0, sigma means becomes 0, the stress pattern will be like this. So here you can see that sometimes the stress is positive and sometimes it is negative. So positive sign is for the tensile type of stress and negative sign is for the compressive type of stresses. Okay, so you can see that the stress amplitude, sometimes stress amplitude is positive and sometimes stress amplitude is negative. So when the sigma mean becomes 0, the stress pattern becomes the completely reversed type. Okay, so the load will not be of fluctuating, it will be of reversed stresses. Okay, reversed stress type. Okay, so in this case the criteria of failure is the endurance limit, that is SE. So when the load is of a completely reversed type, the criteria of failure will be on the basis of endurance limit. You can see that on the y-axis, on the y-axis, that is ordinate, endurance limit is plotted. Okay, So when the component is subjected to both components of stresses, that is the component, there is a mean stress acting on the component, and sometimes the mean stress becomes zero. So in that case the component is subjected to both fluctuating and reverse stresses. Okay, so in on the component there is a mean stress sigma A is also there, and stress amplitude is also there. So in that case, when the component is subjected to such type of component which is subjected to, which is having the mean stress and stress amplitude also, the failure occurs at different scattered points. So let me show you, or let me highlight the scattered points. Okay, so these are the scattered points. So you can see that these are the different failure points. So these are the failure points which are plotted for the component which is subjected to, which is having the mean stress also and stress amplitude also. Okay, so in that case these scattered points are actually dividing or they are creating two regions. First is the safe region, and second is the unsafe region for various combinations of sigma m, that is mean stress, and sigma A, that is stress amplitude. So for the various combinations of sigma m and sigma A, so here you can see that as the sigma m goes on increasing, the sigma A is decreases. Okay, so initially when sigma m is less for the some few values of mean stresses, but for the higher endurance limit, you can see that these are the failure points. So here different criterions are proposed to construct the borderline dividing the safe zone and failure zone. Okay, so they include, first is the Gerber line. Let me highlight the Gerber line with a different color. So here you can see that this is the Gerber line, this is the parabolic curve, it is the Gerber line. Okay, and second is the Soderberg line. Okay, so this line which is highlighted by the green color is the actually it is the Goodman line, sorry, and third one is the Soderberg line. Let me show you by a different color. So this is the actually Soderberg line. Okay, so these three lines they include or they are used to divide the safe zone and unsafe zone. So let us see one by one. So what is Gerber line? So the curve which I have highlighted by the red color, which is having some parabolic type of pattern, so it is the Gerber line. So actually Gerber line is the parabolic curve which is joining SE, that is endurance limit, which is plotted on the y-axis or the ordinate, to SYT on the SUT, ultimate tensile strength, on the x-axis, that is the mean stress. Okay, or it is the abscissa. Okay, so this parabolic line is called as a Gerber line. Second is the Soderberg line. It is the straight line. Here you can see that Soderberg line I have shown by the blue color. Okay, so here you can see that the Soderberg line is the line which is joining the endurance limit on the y-axis, that is ordinate, to the yield strength in tension on the x-axis, that is the abscissa. Okay, and third is the Goodman line. Here you can see that I have highlighted the Goodman line by green color. Okay, so here it is the straight line which is joining SE, that is the endurance limit, on the ordinate to the SUT, that is ultimate tensile strength on the abscissa or on the x-axis. It is called as a Goodman line. Okay, so here students, the Gerber parabola, you can see that the Gerber parabola actually it follows the failure point. So you can see that it fits the failure points of the test which is conducted for the combination of fatigue and cyclic fluctuating stresses and the component which is subjected to both types of stresses, that is sigma and mean stress, which is having mean stress and stress amplitude. Okay, so here The Gerber line follows or it fits the failure points which are plotted practically by using a test. Okay, so here the Goodman line, here you can see that the Goodman line actually it fits beneath the scatter point. It is the line green line which is highlighted by the green color. It is actually it fits beneath the scatter of this data. So both Gerber parabola, the line which is shown by the highlighted by the red color, and the Goodman line, the green one. Okay, these two lines are intersecting actually at the SE on the ordinate, that is endurance limit on the y-axis, and SUT, that is ultimate tensile strength on the x-axis, that is abscissa. So however, the Goodman line is considered as more safe comparatively the Gerber line. Okay, why it is more safe? Because it is completely inside the failure points. Here you can see that actually the Gerber line follows the, actually it fits the failure points. Okay, and here you can see that the Goodman line is exactly situated below the Gerber line. Okay, so it is inside the failure points, it is away from the failure points. Okay, so it is inside the safe region. So that is why it is for the design considerations, Goodman line is more safe from the comparatively the Gerber line. Okay, the next is the Soderberg line. Here you can see that the line which is highlighted by a blue color. Okay, so here the Soderberg line is more conservative failure, having the more conservative failure criterion, and there is no need to consider even yielding in this case. Okay, so yield line is constructed. So here you can see that a dotted line is there. Okay, this is the yield line which is constructed connecting the SYT, that is yield strength in tension, on the both axes. Okay, so this is the yield strength in tension on the x-axis and yield strength in tension on the y-axis. So this it is called as the first limit, or limit on the first cycle of stress. Okay, so this is because if a part yields, it has failed regardless of its safety in fatigue. Okay, so next I am going to apply some equations. Here you can see that we have one parabolic curve and two straight lines. Okay, so I am going to apply equation of straight line for Soderberg line and Goodman line also. Okay, so let us apply equation of straight line for Soderberg and Goodman line. So this is the equation of straight line: x upon a plus y upon b is equals to 1. So where a and b are the intercepts of a line on the x and y axis. Okay, so a and b are the intercepts of the line on the x axis and y axis respectively. So let us apply the above formula, the given formula equation for the first is, that is the Soderberg line, for this line. Okay, so let us apply the equation. So for the Soderberg line, the equation becomes sigma m divided by SYT plus sigma a divided by SE is equals to 1. So here sigma m is the mean stress, which is the average of maximum plus minimum stress. Okay, sigma a is the stress amplitude. Okay, SYT is the yield strength in tension. Okay, which is the line starts from SYT and it ends at the endurance limit. Okay, so SE is the endurance limit. Okay, similarly this I am going to plot, or I am going to write the same equation for the Goodman line also. Here you can see that the Goodman line is, it starts from endurance limit SE and it ends at the ultimate tensile strength on the x-axis. Okay, so let us write the equation of straight line for the Goodman line. The equation becomes sigma m, that is mean stress, divided by SUT plus sigma a, that is stress amplitude, divided by SE, that is endurance limit, is equals to 1. Okay, so the Goodman line, here you can see that in the previous slide I have said that the Goodman line is widely used as a criteria of fatigue failure. Okay, so when the component is subjected to mean stress, that is sigma m, as well as the stress amplitude sigma a. So there are some reasons behind that why the Goodman line is widely used. So first reason is the Goodman line is safe from the design considerations because it is completely inside the failure points of test data. Okay, students, let me highlight once again. So these are the failure points. Okay, and you can see that the curve which is passing through the failure points is nothing but it is the Gerber line. Okay, and you can see that the Goodman line is situated below the Gerber line. Okay, so it is in the safe region from the design considerations because it is completely inside the failure points. You can see that Goodman line is completely inside the failure points of the test data. Okay, second is the equation of straight line is simple comparatively. If you will go for the Gerber line, it is having some parabolic curve. Okay, so the equation of parabola is quite difficult comparatively the equation of straight line. Okay, so it is simple, so that is why we are preferring the Goodman line, because it is for having a straight nature. It is having the pattern like a straight line. Next is, it is not necessary to construct a scale diagram, and a rough sketch is enough to construct the fatigue diagram. Okay, so these are the some basic reasons why we are preferring the Goodman line over the Gerber and Soderberg line. Okay, okay students, thank you.